So in the previous slide, we looked at a very simple summary variable, summary data, summary table. And as I said, it does not show any relationship between these two variables. It's just a single variable by a single variable. And to study the relationship, what we need is the relationship. When the student class size is reduced, how much test score increases. And to study the relationship, you need to look at the scatter plot to see the direction of the relationship. For example, this is a scatter plot. Also, it's what I taught in 320. So there are 420 dots on this graph. And you have to find pattern. It's unclear. From this graph, it looks like there is a negative relationship, but it's unclear how steep or how flat the curve the trend is. And but negative downward sloping slope is it makes sense because the larger the class size is, the worse students' performance is. So as you, or in other words, if you reduce the student teacher ratio, uh, then your students will do better. That's what you want, and that you want to quantify that. So the graph analyst kind of verifies the negative relationship, downward sloping relationship. But what does it mean? How can we interpret? How can we quantify this? We would like to look at the data more carefully. And now here we need to use some methods, serious, rigorous statistical methods. We typical three ways of doing this is like estimation, hypothesis testing, and confidence interval. You learned all of them from 320. So estimation is simply estimating the difference, the how much the class size increases the test score by one number. So the number is the estimator. So that is estimation. And hypothesis testing is to test hypothesis. Like for example, the null hypothesis you want to test is that class size has no impact on test scores. If that hypothesis is rejected, then you can accept that the reduction in class size will have some impact on test scores. So that's another statistical methods and a possible way to prove the relationship. And finally, the third is to give an interval. So the difference, the effect, will be somewhere in between these points. Like say, reduction by one student per teacher would increase the test scores by somewhere between 10 to 20 points, for example. Then the 10 to 20 points is referred to as the confidence interval. You are confident that the difference lies between these 2 points. So that is an interval. So we call that confidence interval. When I taught 320, I bundled estimation and confidence interval as one chapter. So basically they're the same thing, estimating by 1 point or by an interval. So the point here is, now I'm just briefly reminding you of these terms, and if you are not confident you learned it, then I strongly encourage you to do something, take some actions. You are going to use these terms to study other later models that come later. So, and let's do a very simple toy model analysis. At the very simple level, we are going to classify the data into two groups. Well, simply there is no reason, but we cut the student-teacher ratio at 20. So below 20 is defined, labeled as small class, and more than 20 is labeled as large class. Of course, you may ask why 20 it matters. There is no answer to that. It's ad hoc classification, but like at this point, keep everything simple and simply see what happens when you group the observations into small group and large group. And then for each group, you can calculate the average score. Small group has 657 points average, and large group has 650, about 7.4 difference. And standard deviations also different, and sample size different. So let's go back to the scatter plot. So you cut the data at this point on the right side and the left side. So divide the data into by this line, and calculate average for these guys, and you obtain these numbers. From these numbers, you can do all the methods like estimation. You can estimate the difference between these two groups in their averages, and test the hypothesis that these two groups have no difference. So delta is 0, which means there is no difference. And you may construct a confidence interval for delta. So the delta is the difference. So where the difference would lie. So the methods can be applied to here. I'm not going to teach you how to do that. I'm just reminding you what we have done. So estimation is simple. Simply if you remember, the mean is the sample average is the best estimator for the population mean, the best estimator. So in this case, you simply take the difference when you estimate the difference of means, estimate that by difference in averages. So just average. This is average of small group. This is the average of large group. And the difference is 7.4. So even though the equation looks more complicated, but this is simply the difference here, right? So you can tell that the difference is 7.4. That's the estimator. But the problem is 7.4. How large is it? How large is it? You have to interpret that. So from there, it's not about statistics, but it's more about economics and your subjective decision. Like you may compare this 7.4 to see how large it is. You may compare that to the standard deviation. Standard deviation across district. So the whole standard deviation was 19.1. It's much smaller than the standard deviation. Or you may compare this to this difference. For example, the difference between 60 percentile and 75 percentile is 8.2. So the difference is even smaller than that. So reducing the class size from large to small will change your school from top 40% to top 25%. Actually, the effect is less than that, but it's comparable. You put the number in some context. So then still, even if I give you these numbers as comparison, but still it's not enough. You have to interpret more, make more judgments from there, but that's beyond statistics. This is how we utilize the estimator. And hypothesis testing. Hypothesis testing, if you remember, in testing hypothesis testing, what we did is we first calculated the t-statistic. In my class, in my 320 class, I explained t-statistic as the standardized difference between the sample mean and your hypothesis, right? So what you have the difference between what you observe from the data and what you believe in the hypothesis, and that is standardized by the standard error. That is the t-statistic. We do the same thing. So on top, we have the observed difference, right? Observed difference, and it is standardized by the standard error of itself, right? And standard error is calculated this way. So I'm not explaining why we get this. That's from 320, but the idea is the same. Based on this t-statistic, if t-statistic is close to 0, that means the data and the hypothesis are more consistent. But if t-statistic deviates from 0, like too large or too small, then that means your data and your hypothesis have some differences. So then you have to worry about why there is the difference. The difference may be because of random errors or maybe because of wrong hypothesis. So that's how we that's the framework, how we understand the hypothesis testing. And in this case, in our data, you can apply that. So the difference, you observe the difference of 7.4. 7.4 is the observed difference, but your hypothesis is that they are the same. So suppose that the null hypothesis is that small group and large group has no difference, or class size has no impact on the test scores. So then the observed difference is 7.4, and in the denominator, you need to standardize what you observe by the standard error of this this number. It is 4.05. And as you remember, the t-statistic approximately follows a normal distribution, standard normal distribution, and 4 on the standard normal distribution is a very large number. So it happens with a very small probability, and if you use 5% significance level, you need to reject the null hypothesis. The threshold is usually 1.96, so null hypothesis is rejected, and it implies you get a strong conclusion that the class size has statistically significant impact on test scores. That's the conclusion of this method. And finally, confidence interval is calculated by point estimator. Point estimator is the mean, sample mean, plus minus z value times standard error. And z value is coming from the standard normal distribution, and standard error is the same standard error we used before, and point estimator is the mean. So the answer is 3.8 to 11.0. So the estimated on the average difference is 7.4, but this number 7.4 may have some random errors. So you allow a certain margin of error. The margin of error is calculated by this way, using the standard error and standard normal distribution table. So as a result, you expect that the difference could be somewhere between 3.8 11.0. So it would be greater than 3.8 and smaller than 7.0. And this confidence interval is 95%, which means you are confident that this interval is true with 95% probability. 5% error probability exists. And the confidence interval is actually kind of dual problem to the hypothesis testing. They have very similar structure, like confidence interval and critical values have they are mirror image, and confidence level and significance level are also mirror image. So when you learn these two, then you should be able to compare and see the difference between hypothesis testing and confidence interval. Okay, I'm going to stop the video here and resume in the next one. See you there.